somebody was saying was maybe the is we can just have them sit right there with a piece of paper and a pen, and they can write the essay right there in the class, and you can watch them. So I don't know. That's where we are. Govind, I see close to 3:30 here.
Yeah, okay. It's 3:30 now. So let me see if they can hear us. In Gargar 101, can people hear me?
Yeah, we can hear you.
Yeah. Okay, so you can hear me. Okay, Wayne. So if you want to go ahead and introduce the speaker, I think
sure.
we can go from there.
Yeah, I know. So, well, some people are so much fun to be around. We don't even really have to have a cloak, and we can just talk and have a great time here. But SK Sundaram, I'm so happy to have you today with us, even virtually here. Is Indamori Professor of Material Science and Engineering, and endowed chair at Alfred University, which is only about an hour and a half away. It's to the south of Rochester. He's also a chair of material science. And before joining Alfred University, let's see my bio. Hang on a second. View just changed here. Let me get my bio back again. Okay, yeah. Before joining Alfred University in 2011, he was chief material scientist at Pacific Northwest National Laboratory. And he got his PhD technology in 1994. In the past 22 years, he's made major contributions in the area of millimeters, terahertz wave science and technology, ultrafast material science, happens to be my favorite, engineering, multi-scale materials processing, and infrared materials and devices. He's a fellow of many, many societies, too long of a list to mention, and we welcome him today. Thank you, SK. Please go ahead.
Thank you so much. Good afternoon, everybody. I hope you all can hear me. First of all, I apologize for not being physically be there to present. I would have loved, but I'm still being a little overly cautious. I have two senior citizens living with me right now, so please bear with me. Before I start my presentation, I would like to thank Professor Knox and Professor Agrawal for the invitation and making arrangements. And I also appreciate Lynn for all her communication and also making these arrangements to make this seminar possible. With that, let me start my presentation.
Could you make it full page? I mean, the full screen? Okay, good.
Yes, I just did that. Thank you. As you know, my name is Sundaram. I'm an Indamori Professor of Material Science and Engineering here at Alfred. The talk I'm going to give is almost entirely of Nicholas Tostanovsky. He was a PhD student who just graduated about 3 months ago. He's now Dr. Tostanovsky, and he's at Koning, and you will also see me acknowledging him again at the end. Let me start with the overview. I just want to give you an introduction and background about our motivation in this area, why we are doing what we are doing, particularly looking at glasses for this application in this frequency region. I will talk a little bit about terahertz region, but I will really focus on two things, a little bit high level I wanted to communicate to you. One is structure terahertz property relationship in glasses. This is one of the things material science community is very interested in always exploring is, I want to know the structure of the material. I also want to know how that structure will control a specific property I want, so I can design the structure to get that property I want. So we studied a few glass families. I'm going to talk about borosilicate, which is, we call it as a common oxide glass. And I will also talk a little bit about chalcogenide glasses. These are non-oxide glasses. Both are a significantly different group of families. I just wanted to show you how we could compare the terahertz properties of these glasses. At the end, I also wanted to show you our high-level results of borosilicate, tellurite, and chalcogenide glass families, and also come up with some correlations we have come up with based on our data. With that, I will summarize what our finding. Back to the motivation. We were looking at the literature 5 years ago. We found a few results reported on terahertz properties of common commercial glasses. So we thought we would try to locate, is there a comprehensive study out there, particularly on silicate glasses? These are common glasses, soda lime silicate, borosilicate. We could not find any full comprehensive study tying it to the glass structure. So we thought we will start our own, and we will measure terahertz optical properties. By that, mainly I'm talking about refractive index and the absorption coefficient of these glasses, and collect data and then put together this structure-THz property relationship for select glass families, and present and also publish this work. We also did use femtosecond laser pulses to modify some of these glass compositions locally to see whether I can also change terahertz properties by using femtosecond pulse laser. The idea behind that is I will use laser pulses, I will deposit certain level of energy locally, which will, part of it will thermalize and it will change the glass structure in the location. Then I'll be able to track the changes and properties. If I can do that, then not only I can make a specific glass composition, a piece of glass with the specific terahertz properties, I may be able to also locally modify it by using femtosecond pulse laser or any other means of processing tool. Just to broadly describe, 0.3 to 30 terahertz is officially sort of a defined terahertz region. It has been at the heart of many physics and the biology and chemistry discovery, and over the past couple of decades, it has got more attention. And as we all know, electrons in the orbital level orbit, and the small molecules rotate at terahertz frequencies. And there are semiconductors and nanoscale semiconductor structures resonate at terahertz frequencies. And some of the blackbody matters emit blackbody radiation about 10K at terahertz frequencies. So there are a lot of things happening if you look in that region. And we are, of course, more interested in materials and behavior. And there's two roadmap and the scientific report I'm showing on the screen are very informative. They have brought in some of the best mind in the field together, a roadmap, and also see where this field is now, where it's going. You may want to check that out for broader appeal, but I will be talking mainly about materials again. And the terahertz spectroscopy and imaging tools have matured over a period of time. And now you can buy with a reasonable price tag, completely packaged spectroscopy or imaging tool for your lab. It has got some limitations in terms of how far you can measure, but it allows middle science community like me to use this as a tool and study my materials. There are many ways of measuring terahertz properties, quasi-optics and many, many techniques, but we have chosen a terahertz time domain spectroscopy, which is for various reasons. Number one, the instrument is available. I could buy using my startup about a decade ago. And also I can use the time domain spectroscopy to extract directly from the experimental data set, real and imaginary part of optical and dielectric constant. So I can basically measure refractive index and absorption coefficient of any composition I can manage to put together. So that was our initial decision. And we also followed a major study by Naftali et al. This is a group at National Physical Laboratory in UK. They were the first one to actually publish refractive index and frequency over a range of terahertz frequencies of selected glasses. So you would see some of the BK7, zinc, crown, Pyrex, and the silica, these glasses shown. You can see, first thing it probably strikes you is where is resonance? I don't see any resonance here because these are all disordered glass structures. But the good news is you can see there is a chemistry-dependent refractive index. You can see a whole range of refractive index for various glasses. So we may not be able to capture some specific resonance because there are not rotational, those symmetries happening in these materials. But we'll be able to measure the properties directly. Another thing I want to point out is in material science, again, the terahertz properties all depend once again on polarization ions present in the glasses. polarizability, as you know, in the visible range. Most of it is predominantly to do with the electronic polarization. But when it comes to terahertz properties, both electronic and ionic contributions contribute to the property we are measuring. And then we were looking at the literature. There is also a Storm and Sloman power law. They come up with a product of refractive index and absorption coefficient as a function of frequency can be equated to a material property K with an exponent of beta, which can be tied to glass composition. So this is one of the things we also want to explore and see how good this power law applies to specific glasses we have made in our lab. And broadly, there's many applications of terahertz technology, anywhere from you can use some of these materials as a passive windows or lenses and waveguides, and also active interrogation of certain signatures. Some of these materials will be useful as a passive or active components. Broadly, there are many areas of astronomy, remote sensing, national security, where terahertz applications are dominant. I've shown you various polarization mechanisms, and you can see where the terahertz frequency lies. The spectroscopy we have at Alfred is TPS Spectra 3000 system. It's packaged by TeraView and marketed by that. It has access to about 0.06 to 4 terahertz spectral region. It doesn't need any liquid helium cooling or no vacuum system. Really fully packaged. We could collect spectra in a few minutes time at ambient temperature. We could also possibly heat or cool the sample holder to measure properties as a function of temperature. This is the view of the instrument in our lab. You can see here, if you can open this lid, that is where you can put your glass sample. The detection is based on the terahertz wave generation and detection both depend on structured gallium arsenide semiconductor-based antenna approach. So terahertz waves are generated below this inside the box using ultrafast pulse laser, and they're guided through the sample holder inside. Once you put your sample in, you can let the terahertz wave pass through. In the transmission mode, you can measure the properties, and you'll be able to plot a real and imaginary part of the optical or dielectric constant from the same data set. The same terahertz waves can also be guided using optical fiber mode here. There's a fiber going back to a scanning mode where it's connected to your head, and that can be used for scanning large-scale samples. And as you know, because of their long wavelengths, these are really useful only for scanning large-scale defects in structures and materials, not for atomic scale inquiry or atomic scale studies. Typically what you get is you start with the terahertz signal, and our first Fourier transformation, you can get terahertz electric field, and from there you can extract the absorption coefficient spectrum and the refractive index spectrum. You can see this is just a raw data of simple glass, a piece of glass we put inside. We use the reference nitrogen gas, high purity nitrogen gas. You can see how you can collect the data spectrum and the data set, and also plot absorption coefficient and refractive index over frequency range. I want to point out to you about the noise floor. Often our spectrometer can go up to even 4 terahertz, but really the sample dictates how much we can measure the sample chemistry, the sample structure. So often we hit the noise floor between 1 and 2 terahertz. So you would see our measurements are limited to that range, beyond which we could not differentiate the noise between the measurements. Just one slide to show there is plenty of research going on femtosecond pulse laser glass interaction. They have complicated interactions. Many phenomena have been studied by groups. You could write, depending on laser parameters, various components in piece of glass or layers of glass. When you deposit sharp, tightly focused femtosecond pulse laser, several nonlinear processes go on inside material, inside glasses, just like in any lattice. Further into the irradiation, a significant part of the radiation sometimes get thermalized, sometimes they are not. For the gloss, at least, we noticed the repetition rate is a big variable for us. The low repetition rate is close to single pulse laser level you can go. You can try to squeeze and modify material without paying a thermal penalty. A lot of thermalization happens. And a high repetition rate, we have a cumulative effect of multiple laser pulses. We end up getting significant thermal effect, thermalization of carriers. All this happen in our material, and the thermal energy is transferred to the lattice and the glass structure, and in the process modifying the structure. The outcome of this is you will be able to measure actually positive or negative changes in refractive index of the modified regions. It could also be isotropic, anisotropic, depending on your writing conditions. All these things have already been demonstrated by several research groups. Based on our about 5 years' work, we have published about 8 papers recently between 2022 and 2023 now. These are all current papers from our group. All of them are really on structured terahertz properties of glasses. I won't give you all those details, but if anyone is interested, I'll be glad to send you the PDF of paper, but I will only be picking select results on this highlighted papers, one on borosilicate glasses. It's a silicate oxide glass, and one on chalcogenide glasses, non-oxide glasses. And I will talk a little bit about the universal power law I talked about at the beginning of the presentation. This is the first part of the work on sodium borosilicate. This is published in the International Journal of Applied Glass Science. Borosilicate is a well-known commercial composition, but for non-glass people, it's not a single composition. Whenever we say borosilicate, that's a family of glass compositions of varying mixture of all these components. That the 3 major components in borosilicate glasses are SiO2 silica, B2O3 boric oxide, and Na2O sodium oxide. The silica is we call it the backbone structure. That's when you melt silica and quench, you form silica tetrahedra inside the glass. And the sodium oxide or alkali or alkaline earth, we call it modifiers. What they do is they go and break some of this oxygen silicon bonds and making a non-bridging oxygen, in the process depolymerizing the glass structure. And boron plays a double role. It also partly associates with the silica tetrahedra, partly like to be on its own. So it's an interesting mixture of the glass structure you get. Finally, you get a range of glass structure. So we use ratios like R and K. R is a ratio of sodium oxide to boric oxide. K is a ratio of silica oxide to boric oxide to talk about our glass structure. You can see boron can be connected to oxygen and part of the boron ring. This is what we call a Riemann-Generite ring, this structure we find in glasses. And we also sometimes see how boron is connected to oxygen in the network. We call them a Dan-Borite ring. And what we did is we selected these compositions and we made in our lab these glasses. You can see the red dots and the black squares. So we made in our own lab, starting with chemicals, high purity chemicals, mixed them, melted, quenched, made pieces, and solidified, annealed, and prepared our sample. And then we measured whatever thing we wanted to measure. As you recall, I showed you in our terahertz spectra, we are not seeing resonance because we don't expect to see structural responses in those frequency range, but we can measure directly optical properties. So what we were doing is we were using other well-established vibrational spectroscopic techniques to track the structural changes, and then we correlate to terahertz properties we are measuring in these glasses. So we used boron, 11 boron magic angle spinning NMR data. We use infrared spectroscopy, we use Raman spectroscopy to get structural information from the glasses we have made, and then we measure terahertz properties, and then we correlate. We develop this relationship by putting them all together. This is just a sample of our boron, 11 boron spectroscopy. And you can see here, this is 10 mole% of B2O3, and this is 40 mole% of B2O3. You can see gradual change of spectral features here. Let me go back to the NMR spectra here. You will see me using two terminology. One is polymerized network, and another one is a depolymerized network. So when you have 10 mole% of boron, you would see the high R values. We are seeing the ratio, and we start to see predominantly B4, which is 4 coordinated boron we see in the structure, and some of it is connected to silicon, and it's a very interconnected network. When you go to up to 40 mole% boron, we are seeing lower R values, and what we see is a dominant signature coming from 3 coordinated boron and 4 coordinated boron in our glass structure. And so we see a borate and silicate subnetwork. So what happens is when we keep adding more and more boron, it forms additional network species inside the glass, getting more and more polymerized, more and more connected. While we are reducing the boron, it gets more and more open, depolymerized. So we see the similar trend in all our glass families. So I'm showing you now infrared spectroscopic data. We look at various bands, and we know that all those bands are related to specific glass structure here. So I'll walk you through 2 or 3 spectral data. And once again, you will see I'm showing the composition from 10 mole% boron all the way to 40 mole% boron. And I will point out various features in this band we are seeing, and how this is how we can interpret the structure, what is inside the piece of glass. For example, if you look at the 1385 centimeter inverse band, you look at this band here, you can see compositionally the spectral shift. That band corresponds to boron oxygen stretching in borate triangular coordination in the glass. And you can see I will also point out other features later as we go down here. So if you look at the 10 mole%, the depolymerized borosilicate glass, you can see we also see that 1385 barely present here, and that this structure is dominated by silicon oxygen stretching bond and other bonds we see here for this depolymerized structure. So moving on with the same spectroscopy data, if you look at 930 bond, 930 centimeter inverse, this is dominantly due to boron oxygen bond stretching in BO4 tetrahedra structure inside the piece of glass. So similarly, you can see by the time we come to 10%, the shift has happened here. This is dominated by silicon oxygen stretching bond rather than boron oxygen stretching dominating the tetrahedra in the polymerized form. We see the same trend continuing, looking at other features. We are looking at that dominant band here, 1100 centimeter inverse, is connected to the quartz silica tetrahedra that dominates this dominant band you see here. That is the backbone structure of silica SiO4 tetrahedra. You can see that prominently present in all the spectra. And so as soon as you go down to 10% here, you can see the stretching bond. You'll also see some triangular silicon bond here. So you start to see how there's a mixture of silica tetrahedra with the boron trihedral bonding, boron 4 tetrahedral bonding, all these units mixed together at various ratios. Those are the structural species we are looking at. Now, I'm giving you just an example of Raman spectroscopy data. Raman also activates a specific bond of specific members in the glass structure. You can see here again for 40 mole% polymerized borosilicate glass. You can see all the sodium is all affiliated to boron tetrahedra. In this case, this 770 centimeter inverse bond, it corresponds to the 3-membered borate ring, B3 ring, and 1 B4 tetrahedra unit. That's the response you are getting at around 770 centimeter inverse. And you also look at 805, you are seeing a boraxyl rings forming at 805. And you can also see there are signatures at 925 centimeter inverse. There are also some overlaps of the signature. Sometimes we have to do a lot of deconvolution to get some quantification going, but we can clearly see a range of bonds, rings, and structures mixed together in this glass. Okay, that's what I want to get across. But once we also have something going on here is when the alkalis go into the glass, they start breaking the silicon oxygen or boron oxygen, some of the bonds, mainly the silicon oxygen bonds. We start getting things like non-bridging oxygen. Oxygens are loose hanging in the glass structure. So we are very interested in non-bridging oxygen because that dictates a lot of glass properties like electrical conductivity, viscosity, and including optical properties. So we try to tie the terahertz properties we're measuring to R and the modifier and all the structural features we are showing you here. So now a snapshot. I'm only showing you partial results. This is a family of borosilicate. We are showing you refractive index in the terahertz range we measured. And correspondingly, we are showing you how we pick one terahertz value for 0.5 terahertz refractive index, how it changes with the R values, which is the ratio of alkali to B2O3. You can clearly see somewhat more or less very strong linear relationship with most of the compositions. And clearly this says by changing glass chemistry in this family, I can actually vary the terahertz refractive index and also absorption coefficient. Sometimes I'm showing mostly refractive index data, but we also have absorption coefficient data for this from the same data set. So this plot is to let you know we can actually design, now that we know what are the various structural units are present in this mixture of glass structure we are able to produce, and we also know which units dominate in what structure and what is the refractive index we are able to measure. So, we have basically what we have done is we have deconstructed the glass structure and then put it back together and try to tie it to their optical properties we are able to measure. So the conclusion for the borosilicate is our data, spectroscopy data, all suggest we have clearly polymerized network and depolymerized network, and also a various mixture of all these various units. We still have silica tetrahedra, but mixed with also the boron rings and borate tetrahedra, and there are sub-network units. That's what constitute the structure we're looking at. And we clearly see the terahertz refractive index varying almost linearly with the R values, which corresponds to the glass chemistry. So this is one way of putting together a structure, a terahertz property for a family of glass. We have to do this for every family. And then once we put together some of these families, then we can afford to extrapolate or interpolate this data, and we may be able to predict if I select this composition or if you add certain additives to the glass, what kind of terahertz properties I will be able to get it in this system. Now, briefly moving on to the non-oxide glasses, we're talking about chalcogenides. This is a big family of infrared glasses. This family, one of the important application is night vision goggles. It comes from long wave infrared transmission properties of these glasses. These are all non-oxide, that means no oxygen here. What we have done is we have selected simple unary, that's an elemental glass, and we've taken binary, arsenic sulfide, arsenic selenide, germanium selenide, and we also selected ternary, mixing 3 different elements. We selected these compositions, but there is a method to madness here. You can see we have put it again all in a what we call ternary diagram. You can see this is a germanium on this axis, arsenic, and then we're varying this chalcogen element, either sulfur or selenium. So once again, we have mapped our data points where we have picked and all this. Some of the glasses we have made, some of the glasses we purchased, and some of the glasses we also collected from our collaborators. And you can notice one of our collaborators is from NIST. One of the things we wanted to do is we wanted to also compare our measurements to the measurements done in NIST. We wanted to see how close we are. So for the chalcogenide family system, one of the interesting things is they are predominantly covalently bonded glasses. And because of the various chemistry, the layered structure of the glass structure, we see many more interesting range of structural units inside these glasses, anywhere from chains and pyramids and the molecular cages of various combinations of this chalcogenide elements we see inside this glass structure. This is a very well-known family of glasses for various applications. We use this R, value of R, which is we call this average coordination number, because there are various structural units mixed in this glass structure. One way to differentiate and also define the glass is to come up with some kind of an average coordination number we call R. And what we do is we take mole fraction of every atomic element in the glass composition and their coordination number, and then come up with the sum them all up together and come up with an average coordination number. And that's the R number. That's important to see. There's a range of R numbers you will get for all this composition. For example, selenium, 100% selenium is their average coordination number is 2. We use 8 minus n rule. We call 8 minus n rule. N is the number of valence electron in the element. So for selenium, it's 6. So 8 minus 6 is 2. So the average coordination number we can expect for selenium is 2. So this is like one way of bookkeeping for us to keep track of which are the elements getting coordinated in my piece of glass. So I just showed you all these things. And once again, we used Raman spectroscopy to look at structural features of the chalcogenide glasses. We used terahertz time domain spectroscopy. We measured in our lab. Then we also measured selected glasses in NIST, a very similar frequency range. We also used 1 femtosecond laser system, and NIST has with 1 kilohertz repetition rate, 800 nanometer beam wavelength, about beam diameter of 3 minutes, and we radiated these glasses for 5-minute duration. This is some of the things we did, but I want to show you what really happened to terahertz properties. The first slide I want to show you is to let you know we did compare our data set with the NIST data set. I'm showing you 2 different data sets for arsenic selenide and arsenic sulfide. The red curves are what we collected at NIST, and the black curves are collected at AU. And the delta is we compared at various frequencies or selected frequencies for all this composition. How much is the variation of the value we are finally measuring in these 2 different instruments? It turns out that the error limit is all within around predominantly less than 1% in all of our measurement, except in one case. So this is one way to let you know glasses prepared anywhere can be tested somewhere in a standard lab. We wanted to make sure that the features we are seeing are reproducible in another instrument. So here, in the next couple of slides, I will show you once again the Raman band of the chalcogenide glasses right next to the terahertz refractive index property we have measured. Once again, you will see we are able to map the various bands we see, and we are able to also compare various compositions with various R values. That means the coordination number is changing when I'm changing the chemistry of the glass. By looking at this various signature, I can recognize the arsenic, yes, 302 pyramids at 152, 219, at various bands I'm seeing. And whenever I'm looking at sulfur-rich side of arsenic sulfide, I'm seeing more chains and rings and linkages, while I'm looking at arsenic-rich side of the composition, I'm seeing stoichiometric, close to stoichiometric ranges, and predominantly pyramidal structures I'm seeing here. So you can clearly see we can use this spectroscopy technique to exactly recognize what are these various structural components present in the glass, and then we can look at that terahertz properties of these glasses. So you can clearly see with the coordination number, with coordination number changes, the refractive index, terahertz refractive index also increases with the coordination number. So that gives you clearly the idea by also varying glass composition, we can actually not only play around with the coordination numbers and structural units, I can actually get a range of terahertz properties out of these glass families. So if you look deeper inside, we'll be able to look at the cages and chains, all the structures, which we can recognize using vibration spectroscopy. But at the end, optical community may be interested in, if you want to get a glass with a refractive index of 3, with this absorption coefficient, what will be the glass I can use? So these are the data set which will help you to target such a property specifically in a glass family. What we did, we took the data set and we wanted to map it out, how the terahertz, 1 terahertz refractive index changes in this ternary composition diagram. You can see by looking at this diagram by color codes, you can see how the terahertz refractive index can be mapped over this composition. And the one on your left is we are showing the 1 terahertz data set for all these glasses as a function of the average coordination number. And you can clearly see several sharply well-defined linear trends for arsenic sulfide, arsenic selenide. These are well-known chalcogenide glasses. But then there are glasses which the trends are not that obvious. So, but we wanted to just plot everything to show you how some of the glasses, binary simple glasses, fit this trend very well, and some of the glasses are not so well. But you can see there are still several linear fits with the decent R-square values here. We are also showing you how for various arsenic sulfide and selenide composition, when you change average coordination number of these glasses, how the refractive index delta n changes as a function of composition. So that gives you also an idea how I can tailor the composition in this by mixing this triangle and get the composition I want. So moving on to the next slide, this next slide I'm showing you, it looks similar, but if you notice here, I'm plotting terahertz refractive index corresponding to 1 terahertz to long wave refractive index or IR refractive index. This is more like a correlation rather than fundamental relationship. People are interested in, if I select a family of glass, can I use for double purpose? Can I use them if I have the right refractive index values and absorption losses? Can I use for long wave IR as well as terahertz using the same glass system? So this is one example. We did a lot of this correlation in borosilicate glasses, correlating visible refractive index and absorption coefficients to terahertz refractive index and absorption coefficient too. We found a lot of good correlations there. But for the chalcogenides, because they have high transmittance values, they're highly transparent in long wave IR, we picked up the long wave IR refractive index values and correlating to terahertz values. So that you see for certain families like arsenic sulfide, arsenic selenide, they have a pretty good linear trend happening. That means we can correlate one property in one frequency range to corresponding property in another frequency spectrum in the same family of material. So this will also make a material multifunctional. This is one of our goals, is can we recognize what are the other optical functions potentially these classes can be used. Chalcogenides have been so far commercially used mainly for a long wave IR application. But now this may give you some ideas. Some of the chalcogenides glasses potentially can also be used for terahertz other signature identification, integrated photonics, possibly. All this are possible. So once again, we have also measured the delta n in the system as a function of composition, and we are plotting average coordination number of various structural units. So that gives you clearly that we can indeed vary various glass mixtures. We are getting structural mixtures in these glasses, and we can basically tailor a whole range of terahertz properties and also other properties like long wave IR refractive index. So coming quickly concluding that, so you can see we have evaluated our spectral data, and we have confirmed with the NIST data, we have got a pretty reproducible data set for these glasses. And we could see you have fantastic correlation between the average coordination number of structural units we are seeing in these various glasses to terahertz refractive index as well as long wave IR refractive index. We did a lot of laser radiation studies. We are still analyzing some of the results, but at least for the chalcogenide family, we saw minimal structural changes, and also we saw minimal refractive index changes when we laser irradiated these glasses. And it's a very complicated reason. behind why we are seeing minimal changes. Chalcogenide families are also notoriously known for various nonlinear phenomena when you apply ultrafast pulses to them, anywhere from photoabsorption to various processes happening inside, and they also photoself-anneal during even storage at room temperature, depending on how much light they're exposed to, because of a narrow band gap and a whole range of band gap engineering possible with these materials. So I hope this gives you a little bit broader idea of how a non-oxide glass family can be used for a wide range of applications. This is the last part of my talk. Remember, I showed you a universal power law. Can we connect everything, refractive index, absorption coefficient, to some kind of a material parameter and some kind of a glass parameter? So it's like unified theory, but we want just a power law kind of approach and use it for predicting specific optical properties. So what I'm showing you is we also measured a whole family of tellurite glasses. These are tellurium containing rare earth containing glasses made in our laboratory. And you can see, I've shown you the refractive index and absorption coefficient of all the glasses we have measured. And you can see some of them have cut off the noise floor for various ranges. In chalcogenide, we could measure a little bit extended range. And for tellurite, the cutoff is even a little bit narrower here. But the important thing is you can clearly see three families, somewhat more or less distinct families with a distinct set of properties in the terahertz frequencies we are talking about. And I will show you a couple of more correlation, and you will see some grouping happening here, okay? So now I have plotted absorption coefficient versus refractive index for these glasses, and you can clearly see their clumping and grouping of these glass families. So you can see here, you at the left corner, you have the borosilicate and the chalcogenides, somewhat overlapping, but at the high end here, all the tellurite glasses are to the higher end of it. So obviously the tellurite glasses also containing rare earths, heavy elements, and high polarizability, and that's also tied to why we are measuring high refractive index in these frequencies. But this one shows some clumping of the data, but the thing it brings out to you is we at least have two distinct family, this overlapping family to focus on. So now you can use this data set like this to decide if you want high absorption and a high refractive index, or I want low absorption and low refractive index, what composition I should be really using for my glass. So depending on whatever your optical application may be, the absorption level and the loss and the refractive index, then you can go to a correlation like this and try to guess which glass I can use and which composition I can tailor to get the property I want. And now we used all of our data set and we plugged into this power law relationship, and we are showing you the refractive index time absorption coefficient as a function of frequency. And we wanted to extract the K material property and the beta, because the beta was reported to be 2 for all glasses. All the physics journals, glass journals said, oh, we sort of know the power law for glass, it should be 2. So we were also wondering why 2. We're trying to find out, and we found out it's really not entirely true. When you start looking at various families, the beta values change as well. So we are showing now the K values we calculate for all the glasses, and the beta values calculated for all these glasses from our data set. So you can see for glasses, the beta value is supposed to be just 2. This from the physics, they just come up with the power law fitting. But our data clearly shows it's just not 2 at all across the border. There's a whole range of beta values depending on what glass composition you are looking at. We noticed if you're talking about silicates and purely common oxide glasses, you're probably approaching and you're getting more like 2 value. But if you're looking at tellurite, you are getting about 1.5, around that range. And if you're looking at chalcogenides, because of their layered structure, various combinations of structural units are possible, you're getting indeed a whole range of beta values for that. Okay, so in the K factor, we find again a clear clumping of borates and chalcogenides and the tellurite family separately here. So you can see once again, I can use these fundamental parameters to recognize the group of glasses. I will be able to pick and choose and predict or even design to get the property I want. So concluding that part of it, the fitting parameters were calculated, but our data at least shows one big trend is the borosilicates definitely are, there's a decreasing trend between borosilicate, chalcogenides, and tellurite, if you're looking at refractive indices and absorption coefficient values. And the fitting parameters fit well, but the beta parameter is a very strong function of glass chemistry and glass structural units, anywhere from 0.5 to 2. It's not just around 2, as predicted by the power law, original power law reported in the literature. With that, I wanted to just give a overall summary and give a feel for what I was trying to tell you. Forgive me for my very glass science language. I did less optical language, but because a lot of times you can always buy a piece of glass and put it somewhere and to do like a splitter or a quarter wave plate, all those things. But I want you to stop and think about, oh, what if I want to reverse engineer? I have an optics application for which I want this refractive index along this frequency range with the minimum dispersion, and I want this much absorption I can allow. Then how will I go about either making such a glass or asking glass people to make it for me? So, so the big picture is we have actually put together what we call glass structure and terahertz properties. At least for these 3 families, we have shown what are the structural units present in these glasses and how they affect the terahertz properties we are measuring. And we also found this simple correlations like refractive index or absorption to refractive index in other frequencies like visible range or long wave IR range for chalcogenide glasses. And these correlations will not only help you to select one family of glass to do maybe several functionalities in various frequency regions, and by looking at what range you want to cover. If you want to cover multispectral, then maybe a combination of these glasses will help you to build such a multispectral either detection or kind of some kind of sensing, and you can make these glasses. One interesting thing I want to point out to you from making of these glasses is the oxide glasses, borosilicates, and these are the easiest ones to make. You can make tons and tons of it if you want. You can roll and make all sorts of shapes. You can pull into fiber. But when it comes to tellurite glasses, there are some limitations on how big a glass piece I can make, how homogeneous these glasses. So this is some of the classic glass problem we are aware of. But given the knowledge, we can make uniform glasses with a clear and clean properties. That's something we can do with tellurite. Chalcogenides are the most sensitive to make large quantities. It's easy to make them in thin film. It's easy to make like discs, which goes into this night vision goggles and defense application. But if you want a huge piece of it, it's hard to make it. And if you want fibers, there are a small number of companies can make fibers out of this for you, but they're all very limited chemistries, and partly because you are bringing several elements together. Sometimes endothermic reactions are possible. If you try to melt a multi-element chemistry too fast, sometimes you will end up having minor explosions in chalcogenide ampules, and you cannot allow oxygen into the glass making. So normally all the chalcogenide compositions have to be made inside sealed ampules. And then once you made it, once you certified it, then you can take it out, because once you made the glass, it's not easy for any other external elements to get into it. But while making, you can't have oxygen because oxygen leaves a lot of absorption peaks in the for IR spectra. So you have to practically make it oxygen free. And but the good news is several companies do make chalcogenide glasses of well-known compositions. Some of the composition I showed you, arsenic sulfide, selenide, germanium selenide, you can buy discs of those glasses. So if you want a well-known composition, some of the suppliers can already give you, okay? So that's an easy part for you. But where we come in is you don't have a glass for it, but for your application, because your specific refractive index and zone you are interested in, there's not an easy glass piece to find. But can you make one for you? So that's where we come in. Okay, with that, I want to stop here. I want to acknowledge the work I presented to you is by Dr. Nicholas Terahertz, who just started at Koning a month or so ago. This was his PhD work, about 4 years of dedicated work on measuring terahertz properties and trying to tie into all the structural units we're talking about. And I'd like to thank my colleagues, glass engineering faculty, Professor Monkey, Claire, and Lacourse. My group has, over the past decade, we hosted several PhD students and master's students. Every one of them have helped me in many different ways. Right now, Nathan and Kathleen are in my group right now. Kathleen is working on using ultrafast pulse laser to sort of see, can I surface texture glasses and can I join them? This is one of the projects we're working on. And I appreciate all the support I get from Emory School of Engineering. My professorship is also supported by Kyocera Corporation. I really appreciate that because it allows me a lot of freedom to work and do various things I'm doing at Alfred. Last but not the least, thank you so much for your time. I would have preferred in person giving you this and meeting every one of you. But in view of that, please accept this, whatever I could talk to you, exchange with you. And I appreciate your time. And I also welcome any questions or comments you have. I will try to answer to my best effort. Any of this research data, papers you've seen, if you can get it, don't waste too much of your time. Just email me. I'll be glad to get you all these papers. It's so easy for me to just give it to you rather than wasting more time looking for this. My email address is just sundaram@alfred.edu. Thank you again for your time. I'm open to questions and comments.
Great, thank you very much. And I was just putting my online clapping here. Just a beautiful, very large effort of material science. And it really shows how you're really a spectroscopist as much as you are material scientist, right? And so I just really enjoyed that. Thank you so much. So yeah, well, this is open for questions now. You can also put questions in the chat if you like, or you can just go ahead and ask a question. Any questions? Yeah, go ahead.
Yeah, so I was wondering about this power law that you try to check, and you found that in terahertz range, it doesn't really work very well. So the question I had was, does it work better in the visible? I mean, what is the utility of this power law? I mean, clearly in your case, it doesn't really work very well because it depends on each material. You have different K and different beta. So is that in the visible region or some other region it works better?
Yes.
What is the point of it?
Yes, you are right. In the visible range for silicate glasses, it fits better. So the Naftali group I mentioned to you, they measured commercial silicate glasses like a crown quartz glasses, and they could plot terahertz refractive index as a function of visible refractive index, various values picked up. And they showed there is a linearity, and the linearity is tied to how much polymerization or depolymerization, how much I'm changing a structure using alkali. So they try to simplify for silicate glasses. If I change my modifier, my visible refractive index can be linearly changing with my terahertz. So they did provide that, but no one has looked into does any of this linearity work for other families? Because if you're interested in large values of refractive index, terahertz refractive index, or even visible, you may have to go for more and more polarizing ions, and that means higher and higher refractive index. But will this linear correlation will work. That's what we set out to test. So intentionally, we chose a tellurite system, which we know it's going to show high refractive index, both in visible and all other regions. So it turns out for their linear power law doesn't really fully apply beyond the visible to terahertz correlation. And we are still digging into, of course, what goes into this beta values. One of the ways is we think we couldn't modify our law for various families. And we can even break that into structural units. We can even assign partial structural units, adding up to a beta value. But it's still, we feel it's empirical. That's why I'm calling correlation, because it's not entirely from very fundamental physics. It's sort of correlation, but it's very useful if you want to quickly decide, hey, can I pick this glass and do this with that, really, you know.
Okay, another question?
I have a question. This is Duncan Moore. I'm curious, in the glasses, how much delta N did you have?
Yeah, you can see from the data set, anywhere from 0.1 all the way to even 0.5 and 1, depending on, and of course, in some families, my delta N is as much as 1 or 1.5.
No, I'm talking about when you measure, when you illuminate it, when you hit.
Illuminate it, yes, okay.
When you hit with the femtoseconds, how much?
Yeah. They are like, again, we have set up, they're small and they're like 0.0 something we were measuring. And in the silicate, we measured silicate glasses where the interesting thing is we could find the structural units changing from the spectroscopic data, but we are not able to measure a big clear trend sometime in some of the families. In 1 or 2 families, simpler glasses, we can see a clear trend. Like if you take pure fused silica and have only a little bit sodium oxide, then I'm able to see a trend. So otherwise, it's difficult to measure accurately. And I don't think you probably know, we're also running into sampling. What we're doing is we raster glass surfaces, a specific area, we tightly focus our beam, and then after the irradiation conditions, we have to basically carve out, we literally have to sculpt out these samples and then do all the bulk characterization we are doing. So what happens is in the sculpted sampling, there are radiation irradiated portions and some virgin portions are mixed in that. So we did various sampling techniques to try to better that. So, but we're still looking at smaller changes. But I want to add one more thing. If I don't have to break the irradiated portion into small pieces for my bulk characterization, if I'm writing it like a waveguide writing, then I could probably get much more controlled radiation and controlled writing, and then I could expect a delta N 0.05 and even higher. People have demonstrated in the visible optical. We've done before coming to Alfred, I was in Pacific Northwest National Lab. We've done a lot of writing in chalcogenides. We have shown you can get a significant delta N change based on writing conditions. You can do that. So the delta N we're talking about are actually in bulk, small sampled glass collected from the radiator region and then taken to spectroscopy instrument. So you can see it comes with the sampling, some sampling errors and deconvolution errors. So these are the problems we are seeing. You know,
might I suggest this is a good topic for your next talk when you come back again next time?
Sure, yeah, that'll be great. And one of the things is, I'm pretty sure audience and everybody can think of 100 different accurate way of measuring things.
Oh, yeah.
You all can do, because we are seriously optics limited. I don't have, but I can see, but that's something I will also be excited to collaborate, because we can make all these glasses, but it's no use unless we really work with people who can use these properties for whatever they want to do. And then the synergy is, it's really a feedback loop of what if I want this truncated this property in the can we make this composition? Okay.
Sure. Well, I think we're going to follow up with you on that. Do we have any more questions in the audience, either in Gergen, Kai? Do we have any questions in the audience down there?
I have a question.
Okay.
Returning to the ternary diagram,
Yeah.
with the delta N versus average coordination number. Could you elaborate on what you were seeking to showcase for the data set in terms of there was a few different like the
Yeah.
chemical properties and what you were really getting at for that?
Sure. Thank you for pointing out. And the ternary map we were shown is for delta N as a function of composition. The laser modification part is a minor part, so shown on the side. So you're right that the colored map I showed you is basically feeding the property we have measured for selected composition in that family to a software to predict and extrapolate for other values and plotted. So the reason we wanted to show that is we wanted to show like a map color coded. So you'll be able to see if you go towards one of these apex values, whether refractive index will increase or decrease, you know what I mean? So
Right.
That was our reason to show. So, but the triangle is really to show you big compositional changes, because when you change the stoichiometric ratio of arsenic to sulfur significantly, then the N changes dramatically, really. Okay, but the delta N from photo modified delta N change is much smaller. But for chemistry and modification of composition, that is the map, and those lines are calculated by extrapolating between compositions. So obviously, there will be some extrapolation errors as well. But the idea is to give you a visual picture of how these three elements influence which way you go. You get decreasing terahertz refractive index or increasing. And of course, I have to confess, this has to be actually, the N values have to be finally tied to literally all the structural units we've been talking about. So the ultimate physics of the glass tying it to the property is literally breaking all the structural units we are seeing and even quantitatively measuring them and then tying them all together and then come up with a value, how that is going to affect. That would be the most accurate way of doing. And we haven't done that yet. Hopefully we hope to do it in future, but thank you for drawing attention to that.
Okay,
yeah,
I
thank
think
you so
we
much.
may have one last question here before we wrap up.
Anyone in Gergen with a question?
One last question.
All set here in Gergen.
Okay, I think we're all set. Well, again, SK, thank you so much. And we hope to see you again sometime, and we'll get back to you on that last topic. Bye-bye, everybody.
Thank you, Professor Docs. Thank you, Professor Agrawal. Thank you, audience. I appreciate your time. Have a great day. Okay.
You too.
Bye.